that each row in the periodic table is known as a period. So there are 7 periods. Notice that there are only 2 elements in the first period, hydrogen and helium. That's going to be significant later. So just some things that you can observe about the periodic table. Each column is known as a group or family. Those words can be used interchangeably, and those are numbered 1 through 18. So if we look at our notes, hopefully, again, you've already watched that video, so you are a little familiar with the parts of the atom. We know that an atom has a nucleus at its center. And first of all, this is a Bohr model of an atom, which is not the best one, but it's the best for starting out in chemistry. A atom does not have these exact energy levels, but it helps us understand where electrons are when they bond with other atoms, which is where we're headed. So this whole area is called the energy cloud. The whole area outside the nucleus is the energy cloud. And each of these circles is called an energy level. Or over here, you'll notice it's called an atom shell, maybe an energy level or shell. And actually, now that I think about it, we really don't call it an energy cloud. We call it an electron cloud. Excuse me. So an electron cloud is just this whole area. And then each one of these is an energy level, sometimes called a shell. Okay, so the subatomic parts of an atom, the negative part that's outside of the nucleus is the electron. Again, it's negative. The 2 particles in the nucleus, where the mass of the atom is found, are the proton, that's positive, so P for positive, and the neutron, which is not for negative, it's for neutral. So the neutron is 0. So remember that prefix is for neutral. So speaking of which, we just talked about their charges. So the negative one is the electron. The neutral one is the neutron, which leaves us the positive one, which is a proton. And as we already stated, their locations. So which two are in the nucleus? The neutron and the proton. And the electron is found in the electron cloud. Okay. So what I want to point out at this point is that where the mass of most of the mass of the atom is found, and that is in the neutron and the proton. Those are both 1. We basically made up a unit called the atomic mass unit, or AMU, because I mean they're so tiny that we can't like measure them in grams or such. The electron's mass is basically 0. Okay, it has a mass of next to nothing. So you can see that the mass of an atom just basically comes from a proton and a neutron. Okay, so I'm going to skip over here. Well, no. So let's look at these numbers on the periodic table for each of the elements. Okay, so this number right here is called the atomic number, and that is the number of protons in the nucleus. Okay, so that's the atomic number, or the number of protons in the nucleus. And in a stable atom, the number of electrons is going to be equal to that. Now, here's how I want you to remember that. Protons are positive, right? And so for an atom to be neutral and stable, we want it to have the same number of negative electrons, right? So that it is neutral. Okay? So while we're looking at this box, the letters right here are the atomic symbol or the letter or letters that represent the element. Notice that the first letter is always capitalized. Sometimes there's only one letter, and if that's the case, it's always capitalized. And the second letter is always lowercase. Okay, so we're going to start talking about next time these energy levels. You can't see that. These energy levels, and you need to know that the first energy level can only contain 2 electrons, always, ever, never more. Okay. The second level, excuse me, can hold 8 electrons, and the third level can also hold 8 electrons. And there's actually a pattern that you can see of that in, if you look at the periodic table carefully, I bet you can figure that out, that 288 pattern. So what have we not looked at? So we know that this number at the top is the atomic number, or the number of protons. So here we have the element symbol. Here we have the name of it. And here we have what we call the atomic mass. Okay, and so you might wonder, like, well, why is it not a whole number? And here's why. I want you to see that, for example, with carbon, well, I should go back and say this. Elements always, their number of protons can't change. Okay, so if an element has 3 protons, it's lithium. It can't be anything else. Okay, if something has 4 protons, it's beryllium. Okay, it can change. It cannot change. But the number of neutrons is not necessarily the same in all forms. So as we just said, the number of protons can't change. So carbon is always 100% of the time going to have 6 protons. Okay, but if we look at carbon 12, and if you actually counted these out, you would see indeed 6 protons, and then you would see, oh, but there's 6 neutrons, and that's how they get the 12, 6 and 6. This one, though, has an extra green one, so there's actually 7 neutrons. And here there are 8 neutrons, okay? These are called different isotopes, all right? And so to find the actual atomic mass, they look at all the different isotopes found in nature, and they find the average of that mass based on a weighted abundance in nature. Okay, don't let this confuse you, but I wanted you to just have the explanation. So it takes us to this bottom corner here where it says the atomic mass is the weighted average of the mass of all isotopes of an element. So obviously I need to tell you what an isotope is. Otherwise, that definition won't be very helpful. So an isotope, or isotopes, are forms of an element that have different numbers of neutrons. Forms of an element that have different numbers of neutrons. All right, like we looked at with that carbon. Okay, so these are 3 different isotopes of carbon. Okay, great. So last thing, we know that the atomic number is the number of protons. So that's always easy to figure out. And normally the number of electrons is equal to that. Okay, so if the number of neutrons can change, right, or there are different forms, how do we figure that out? Here's how you do it. Let's just do an example. So let's take boron. All right, so boron, its atomic mass is 10.8. That's the percentage found in nature. We're going to round that to 11. we're going to subtract the atomic number. Okay, so if most of the mass is found in protons and neutrons, they must be right here. So this is the mass of the protons and the neutrons. So 11, if I subtract the number of protons, I'm going to be left with the number of neutrons. Okay, so let's fill that in here in this equation I've written for you. All right, so the rounded atomic mass minus the number of protons, which I guess I could also say the atomic number, right? But the number of protons equals the number of neutrons. So for example, we just did boron, and it rounded, the mass rounded to 11, and then we subtract 5. 11 minus 5 protons equals 6 neutrons. Oh, you can't see that. So for boron, 11, the mass rounds to 11, you subtract the 5 protons and you get 6 neutrons. Okay, let's do one more example. I will let you go. So magnesium, where is it? Magnesium. Okay, we round 24.32, 24. So 24 minus the number of protons, 12, is obviously 12. So for magnesium, 24 is the rounded atomic mass, minus 12 equals 12 neutrons. All right, the Bohr model of an atom. Hope this helps.